Hello, we're here with another demonstration for physics. What I want to talk about today is we're talking about projectiles. And if someone asked me what the central idea of projectiles is, I would say the central idea is that projectile motion, it's the motion of an object that's only being affected by one force, that being gravity pulling downward. And you say the central idea is that that motion of a projectile that we get, right, that motion, that arcing motion that we get, it's really just two motions happening at the same time. It's a constant velocity sideways and then a constant acceleration vertical. And so it's a vertical motion, a horizontal motion put together. You put them together, you get the projectile path. You can take a projectile path and you can split it apart again and analyze it separately. Analyze this horizontal motion separate from analyzing the vertical motion using techniques we already know. And that's the main idea. So I want to show that today with this projectile. So here is my plan. We have already talked about Galileo's law of falling objects. Galileo discovers that when you have an object that has a constant acceleration that starts from rest, that if you look at how far it moves in each successive time increment, so for a falling object, in the first chunk of time, say it falls this far, in the next chunk of time, it's going to be moving faster, right? As it falls, it gets faster and faster, it accelerates. And so it should go farther. Well, it turns out if you look at how far it goes the first time, in the next chunk, it will go 3 times as far. In the next chunk, it'll go 5 times as far. In the next chunk, it'll go 7 times as far. The distance fallen in successive time increments follows the odd integers. It's Galileo's law of odd integers. So we're going to go ahead and I'm going to mark that out here on the board. We're going to say, hey, what if we took this ball and we just dropped it from here? Okay. Then we're going to say, well, I'm going to do this, follow Galileo's law of odd integers. But I'm going to do it in multiples of 7 centimeters, multiples, to make it fit on the board better. So we're going to say, okay, what if we drop this thing? And we'll say in the first little chunk of time, say I drop from that height, it'll go 7 centimeters down. That's to there, right? And then in the next bit of time, it'll go 3 times as far. It'll go 21 centimeters. So 7 plus 21 is 28. And then the next chunk of time, it'll go 5 times as far. So 5 times 7 is 35. 35 down to 28, that would be 63. So we get down to there. In the next chunk of time, it would go 9 times as far. And you say 9 times 7, that is 63, right? And you say, well, if I add that to that, that's going to get me off the bottom of my board. So that's as far as I can go, right? And then you say, okay, so if this distance here is 1 between this, do you see that little red mark there? There, that's 1. Then this is 3 times that distance, and then this is 5 times that distance, assuming I did this properly, right? We'll just double check. 7 and 21 and 35. Yep, sure did. Okay, so this is the motion. It's going to fall from here to here, there to there, there to there, fall in front of the front. And the next one would be, like I said, it would be like way down here, right? 7 times 7 is 49. So if I add 49, oh, actually it'll fit. It'll fit. It'll fit. It'll fit. It'll fit. I'm not crazy. It'll fit. So here, I'll go ahead and add 49 under here. It's just harder with this rail. It'll be right about here. There we go. Okay, so there it is. Okay, now that's the vertical motion. It's accelerating because gravity is pulling down on that object. If I drew this specialized kind of diagram that we call a force diagram, ooh, squeaky marker, or free body diagram, then it would look like this. The only force acting on it would be that force due to the gravitational field, right? So there's nothing shoving sideways on this ball. And if there's nothing pushing it sideways to make it get faster or make it get slower, it's just going to keep going at a constant speed. So sideways motion, if I didn't have any force acting on this ball, it would go just equal distances sideways. So I'm going to go ahead and sketch those in here. And this time I'm going to do it like, multiples of 20, okay? Just to make this easy. So we'll say, okay, so after the first time increment, after the second time increment, after the third time increment, after the fourth time increment, it's not perfect. Okay, there we go. So this is what it would look like at constant speed. Going constant speed, right? And falling, going, right, going faster and faster. So you say, so what I'm going to do is I'm now just going to put those two motions together. And so assuming we start here, after one time increment, we would have fallen this far and gone over this far, so we would be right here. After two time increments, we would have fallen and gone over two time increments, we'd be right there. After three time increments, we'd gone over three increments, so it's where these meet, we'd be right there, right? And after four time increments, we'd have fallen to here, and we'd have fallen, we'd gone over sideways to here, so we'd be there, right? And so you say, hey, if I put those two motions together, what is my path going to look like? Now I'm starting here, so kind of there, right? But then I'm going to go, watch this. Do you see I'm getting that curve out? This is that parabolic curve that we see with projectiles. And we just did the math, right, to see how it should come out using our moving equal distance, equal time. We're going constant speed. Displacement is velocity times time. And our vertical accelerated motion to get those values out. Let's test it out. Now, I've got this ball. We're going to start the ball so it starts there at that dot. Right, that's where it's going to leave this board. Right, it gets there. Here we go. Now I got to get the right sideways speed, but hopefully this will follow really nicely. 3, 2, 1. I think I might have given it a little fast of a shove. Let's try that one more time. 3, 2, 1. Hopefully, right along that curve, we're able to predict the motion using the little bit of physics, just a little bit of physics that we know is enough. How powerful is that to be able to predict exactly how something's going to move at any time? You'll see that we can calculate the position, the velocity, exact angle it's going at any time, right? With this physics that you already know. It's amazing. My first time when I was learning physics back in high school, way long ago, this is what blew my mind. Like back then, it was like, I'm like, okay, I understand that, you know, we can figure out kind of how stuff moves, but I didn't think that I would know and be able to predict precisely how things move like that. Like that I would be able to figure this out, right? With the little bit I knew my junior year in high school. Blew my mind. It's one of the things that really made me think physics is really honking cool, that we can predict things like that.